All right, so last time we introduced the idea of Gauss's law and how this can be a really great, easy way for us to calculate an electric field in certain circumstances. And the key to using Gauss's law is you only want to use it when it's going to help you. So the whole point of that is we've got to find a Gaussian surface, that capture surface we talked about, that would allow me to easily integrate that surface integral of E dot dA. So we've got a couple of qualifications for that. So go ahead and take a look at microtest one while we're sitting here talking. One of the things it says is, okay, so we need to have, there are two very common cases. So we need symmetry so that we can find dA. And a good rule of thumb is just come up with a couple of several different shapes that you know that you're going to be able to integrate. So a sphere, a cylinder, a box, or any of a pyramid, any kind of thing that you can think of that you're like, okay, yes, I can definitely find the area of that. And then use that to figure out, okay, which kind of shape will allow me to calculate the electric field because I need the electric field to be constant. I don't necessarily need the electric field to be perpendicular to the sides, but I do need it to be constant wherever it is. And as we're going to see, sometimes you may have part of the shape where it's constant, but it's zero, and another part where it's constant, but it's at our actual, parallel to the area vector. So one of the hardest things about Gauss's law and using Gauss's law is coming up with that Gaussian surface in the first place. And unfortunately, there's really no other way to do it than just practice. See a lot of different situations. Go, oh, okay, I've seen this kind of thing. I bet this will work. And you'll end up just having to try different things. If it turns out that you can't come up with a surface that will work, or any surface that you can come up with that will be constant on E might be some blobby thing that you can't actually calculate the area of without doing a complicated integral, well, then Gauss's law isn't going to save you anything. So there's no point in really bothering with it. Just go back to the differential equation, just solve it from that. Okay. So what we're going to look at today are a couple of classic examples just to kind of introduce you to the technique. It's not that you need to learn these particular problems. What you need to learn is, okay, how did I decide which type of Gaussian surface I wanted to use for that particular situation? That's the focus I want you to keep in mind. All right, let's get started. All right, so let's take a look at scenario one. For scenario one, we want to find the electric field of an infinitely long wire. Make sure that you're going through and you're filling out the steps as we go through this. As you get more experience, you might decide, you know what, I don't need all of these. But also as you start getting more experience, you're going to realize the problem is getting more and more complicated. And following this procedure can help you stay organized, even when you're out in the real world trying to solve these problems. Okay, so first job is always do a sketch. That's our step one. We're always going to make a sketch. Now I'm going to have an infinitely long wire. So I'm just going to draw myself a wire here. And let's stop and think about what infinitely long means. It's impossible to have an infinitely long wire, isn't it? That doesn't make sense. That's crazy. So when an engineer is considering something infinite, what we really mean is if this is the length of it, and let's say that I'm trying to find the electric field some distance, and we can use anything we want, but let's go ahead and just use D. Well, no, that might be a diameter. Let's use X. So I want to know the electric field at this distance X. What we're claiming is that L is much greater than X. So either the wire is very, 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 very long, or I'm staying very, very close to that wire. And in the case of robotics, that's almost always the case. You're almost always going to be looking for that electric field very close to it because all our parts are right next to each other. So if those conditions hold, then you don't make any detectable error by assuming that the wire is actually infinitely long. Now, this generates some issues, though. If I want to look at the charge on that wire, it would be infinite, wouldn't it? That doesn't make any sense, right? I can't have infinite charge. So what we'll usually use is we'll use some kind of a density. Now, you've probably used densities all your life, but probably the most common one that you've used, we use the symbol rho for, and you had the mass divided by the volume. And so that's a volume density. Well, we can also have a charge density, a volume charge density. We still use that symbol rho because that means a volume. And I would just have Q divided by the volume. Now I'm going to use this symbol here to represent volume because if I just use a V, well, okay, that's usually going to be voltage. and we don't want to get confused as to which is which. So a V with a line through it, we're going to call the volume, and that's pretty common usage in physics and engineering. So this would be a volume charge density, just like this is a volume mass density. And the key thing about this is, if you have a chunk of stuff here, right? And let's say that it's got a density of 5.5 grams per cubic centimeter. Well, no matter what chunk I take out of this, each chunk is still going to have that same density. It's evenly spread out throughout. So anywhere in here, I'm going to have the same density. And that's going to be important for us because most of the time we're going to be concerned only about what's enclosed in our Gaussian surface. So if my Gaussian surface, for example, was a box here, something that looks like this, then the density of the charge within that box would be the same as everywhere else. I would just need to multiply by the volume of that particular box. And I would get a different amount of charge than if I multiplied by the volume of the entire object. But remember, most of the time I don't care about the entire object. I'm only interested in what I'm going to find for that particular Gaussian surface. All right, just to very briefly talk about the other kinds, I might have an area charge density, and we usually use a lowercase Greek letter sigma for that. And that's just the charge divided by the area. What we're going to use for this particular problem then is we're going to use a line charge density. And we use a lowercase letter lambda, Greek letter lambda for that. And that's just Q divided by L. So you can think of this as the charge per unit length. So anywhere along this line, no matter where I take, no matter what chunk I take, I'm going to get the same density. So if I take a 1 centimeter chunk over here and a 1 centimeter chunk over here, they're going to have the same amount of total charge just because the density is the same. That way, instead of having to say, okay, Q is infinite, I better not have a Q in my equation, I can use the line charge density for this. All right, so we're going to come up with an expression for this. So your task then is to come up with a Gaussian surface where it will be constant, the electric field will be constant at this distance x that I'm looking for. Well, there's a number of ones you could use. Let's see which ones might not be good choices. What if I put a box around that wire? So I'm going to try to draw this in 3D a little bit. My 3D art is not terribly good, but imagine I put a box. Well, ask yourself, what does the electric field look like coming out of that wire? Well, it's just coming straight out, right? Radially outward from the wire. And that's true all along the wire. And you may say, oh yeah, great, it's parallel. Yeah, but what about this? That's going to be at a different angle here. So my amount of my electric field that's perpendicular to my area vector, remember the area vector is just one little piece of this, and then coming out from the surface of it, perpendicular to it, normal to it, that's going to change as I go around. So that's probably not a good choice. Again, there's nothing wrong with it. It's just that the integral is so difficult that it doesn't save you anything. Spheres, same problem. In this case, a good choice might be a Gaussian surface that's a cylinder. Now, right now, I've drawn it across the entire line. Don't necessarily want to do that, though, because the line is infinitely long. So I don't need to be concerned about the entire charge here. Since I've got that line charge, I can find the electric field at that point using any smaller area, using any Gaussian surface that I want to use. So let's do that right quick. I'm going to repair my infinitely long wire here. So what if I chose one that looked like, oops, I want that to be in red. So what if I chose a Gaussian surface that was a cylinder that looked like this? And you see that that doesn't cover the entire wire. All right, and then of course this would be the other side coming through like this. Now my electric field is coming out in all directions, and even though at these diagonals, as it crosses that Gaussian surface, it's still going to be constant. It's going to be at a constant angle. And in fact, that angle is simply the angle between, let me draw it from the side here so you can see it. If this is, let's draw the wire smaller. If this is my wire and this is my Gaussian surface, the electric field is coming out like this. And I'm drawing it for a positive charge, but it can be for anything. If it was negative, then would the arrow be the same thing? It's just the arrows would be coming back in. But do you see that if I take the area vector here, so take some small dA, my area vector is going to be there. In all cases, the angle, no matter where I am here, the angle between the area vector and the electric field is going to be 0. And so it's constant from there. So that's going to be a really good choice for us to use when we're trying to find the electric field. All right, so let's go through the steps. And this would be a good idea to have those steps that were on the previous lecture where we had laid them all out in order. You probably want to have those in your flipbook where you can get to them very easily. So our first step then is we use Gauss's law. So this is the flux, and Gauss's law says that that's equal to the charge enclosed, just the charge inside the Gaussian surface, not the entire piece. The charge enclosed divided by epsilon naught, which is the permittivity of free space. So that's one of those fundamental constants. I also know that the flux, by definition, is equal to this. The vector electric field dotted into the area vector. So each little piece of this. And then I'm going to add it up all over the surface. Important thing to realize here, the surface is not just this tube. It's also the end caps. I've got 2 end caps on here. So this is actually going to be 3 integrals, and we'll talk about that in a second. Now, since both of these are equal to the flux, they're equal to each other. Here's a pro tip. You're very rarely going to need to have the electric flux unless it's specifically called for. So it is perfectly okay to just start out with this when you're wanting to use Gauss's law. All right. Now, this total area I can break into 3 parts. So we're going to call this the electric field dotted into end cap 1. We'll call this one end cap 1 right here. We'll call this one end cap 2. Plus the integral of E dotted into dA end cap 2. Plus the integral of E dotted into dA for the tube, the part surrounding it. Get my camera back. There we go. And so it's 3 pieces. So let's go ahead and break those apart. So starting with this one then, I'm going to take that dot product, and it's going to be EdA of the end cap 1 cosine theta of the end cap 1. Well, if this, let's change colors here. This is my dA right here. And so my area vector is actually this way. So you see that it is perpendicular. The angle is 90 degrees to the electric field. Well, the cosine of 90 is 0. So that goes away. Similarly, on the other end cap, change it back to black here, plus EdA end cap 2 cosine theta end cap 2. Same thing over here. If I've got some area, it's going to be like this. And so it's also going to be at a right angle to the electric field, because remember, that's coming out like that. So this one is also 0, and that's really convenient. So the only thing that's going to be left then is I'm going to have Q enclosed over epsilon naught is equal to the surface integral of E dA tube times cosine theta of 2. However, notice that if this is my area vector, here's my surface, that's my dA, my area vector is always going to be in the same direction as the electric field. So the angle between those is 0, and that means that this part is just 1. Now things are looking at something I can actually integrate. So this is integral E dAt, like that. Well, E is constant. We chose our Gaussian surface so that it's constant. If I can't choose my Gaussian surface to be constant, well, then there's no point in doing this. So you already set it up so that it's constant. So you know that I'm almost always going to pull this out. So let's go ahead and rewrite it down here. We've got Q enclosed over epsilon naught is going to equal to E surface integral dAt. Well, the surface integral of dAt is just the area of the tube, right? And so the area of the tube then is going to be let's leave it as the area right here. We'll just leave that as the total area for the tube right there. You're going to see why in just a second. Okay. All right, so that's fine, except that, I set this. I, the human, set this area. And yet I should not be able to control what the electric field is simply because I used a particular surface. Also, I've got the problem that my charge enclosed right now is infinite. And that's going to be a big deal. So let's solve this for E. I'll do this up here. And I get that E dividing the AT is going to be Q enclosed divided by epsilon naught times A. So now let's go ahead and fill in the area here. And let me get my pen back to pen. And so all we need is the area of the tube. Well, the area of the tube is a cylinder. And so that's going to be 2 pi times the radius. We're using the variable x for that. So let's go ahead and keep that symbol. Times the length of that cylinder. Now, here again, remember, we're talking about the Gaussian cylinder here, not the entire length of this. So we're going to go ahead and make that L enclosed. Well, now we plug this in and we get E equals lambda L enclosed divided by epsilon naught times, whoops, let me start to write my A again there, divided by 2 pi XL enclosed. And now you can see what's going to happen. The L enclosed cancels, as it must, because you just created this Gaussian surface, and you're not allowed to change the electric field just because you chose a different Gaussian surface. So even though we use these intermediate variables in between, they need to cancel at the end. And so that's an important thing that's going to happen often when you're using Gauss's law. So our final answer then is going to be E is lambda epsilon naught. So let's say 2 pi epsilon naught times x. Now, you can go one step further if you want. We know that epsilon naught is 1 over 4 pi times Coulomb's constant. So if you wanted to substitute that in there, then E would be lambda, and we'll just go ahead and write it out for now, 2 pi 1 over 4 pi k times x, which is, of course, my 2 pi's are going to cancel. We left with a 2, so I get 2k lambda over x, which maybe is a little bit prettier, might be easier to use. If you're under a time crunch, though, there's really no point in cleaning it up like that. You can plug this number in. Epsilon naught is 8.85 times 10 to the minus 12, and you're going to get exactly the same numerical answer. So the last microtask we want to look at, we want to make sure that this makes sense. All right, if I increase my distance from the wire, what's going to happen to my electric field? No, it's going to decrease because they're inversely proportional according to our equation. But that makes sense. The further away I get, the weaker the magnetic field had better be, or the electric field had better be. Now, what if I increase my charge density? Well, if I increase the charge density, I've also got more charge here. So my electric field in that case is going to go up, which again makes sense. So always do these kind of reality checks to make sure that everything is kind of making sense and falling into place the way it should. So what if I have a sphere? All right, let's make it a great big sphere. Whoops, that's the eraser. So I'm not a point charge, but a sphere. Okay. And let's say that that sphere has some Q. Here's the thing. What if this is a conducting sphere? So I might start out with, a whole bunch of negative charges in here. But the definition of a conductor is that the charges are free to move. So they're going to repel each other. And we've talked about this before, but basically then, let's just make this nice and big. All of these are going to move away from each other. And so in a conductor, all the charge actually lives on the surface. So one of the questions you may find in your homework, and let's just go ahead and talk about this. What is the electric field inside this sphere? So let's make that dash because we're used to drawing our Gaussian surfaces inside. So that's some distance inside. Well, if all the charge is on the outside, let's set it up. So I've got Q enclosed over epsilon naught equals integral E dot dA. How much charge is actually enclosed in here if all of it's on the surface? None. It's zero. So this term right here is zero. Well, the area of that Gaussian surface is certainly not zero. So the only way that this could hold is that tells me that the electric field is zero. And so you calculate that without doing any math at all. Just by looking at Gauss's law, you were able to figure out what's going on. So keep that kind of thing in mind. All right. Okay, so you saw one very simple example of how we can use Gauss's law just by finding the electric field around that cylinder. In your homework, you're going to find some similar cases. Now, for example, if I have a plane, what kind of surface would I want to use? Well, I certainly wouldn't want to use a cylinder oriented this way because that curve isn't going to work. But maybe I could rotate that cylinder to be up and down. Think about it. So the art to using Gauss's law is to figure out what kind of Gaussian surface, that capture surface, what kind of Gaussian surface is going to work that will meet all of your requirements for making the problem easy. If you can't make the problem easy, well, then there's no point in using Gauss's law. Just go back and do the integration manually. All right. All right. Good luck.